This is an example of an AC analysis problem in Circuit Tutor on level 4. So we'll enter AC analysis. And we'll select the first type of problem on level 4. This is going to be an AC source transformation problem. So let's first just show an example of this to illustrate what it's like. So here's a problem. Notice that this problem has been given to us in the phasor domain, which we can see because the impedances are all complex numbers, except for the resistances, of course, which are real numbers. And the source values are given as phasors, namely complex numbers, as opposed to functions of time. So we don't need to translate into the phasor domain or do the phasor transform, but we're going to do source transformations. So first of all, of course, we do simplifications. So here there are two elements in parallel that can be combined, and that will not disturb this sought voltage, V0, because they both have the same voltage. So we can just combine those directly. And remember that when you combine impedances in parallel, that you have to take the reciprocal of the sum of the individual impedances. So it's 1 over 5 plus 1 over negative j8, and then we take the reciprocal of that. And then that can be computed on a calculator to be just equal to this. So that's now replaced by a rectangular box to signify a general impedance. Now there's no more series parallel simplifications that can be done here, so now we need to start doing source transformations. You're not allowed to do source transformations in Circuit Tutor if there are series parallel simplifications that can still be done, because you really wouldn't want to do that if you don't need to. So we now have a voltage source in series with a resistor, and that would be a good candidate for source transformation. Remember that this would also potentially be a candidate, but the problem there is that we want to know the voltage across that impedance. And if we do a source transformation on this voltage source in series with that impedance, we would lose the sought variable of interest. So we definitely do not want to do that. We'll never transform this. Instead, we'll try to get everything else to make this just a single loop circuit. The goal is always to try to get, if possible, a single loop or single node pair circuit. And these problems are actually designed so that you can do that. So here we would transform the voltage source in series with a resistor into a current source in parallel with the same resistor. So we've moved the 4 ohm down here and extended the circuit out a little bit. And we changed the voltage source into a current source. Now notice that the positive side of the voltage source becomes the head of the current source. In other words, we want this to have the same polarity. So if you just think about, say, putting terminals here and here, this current would then go like that, and that would make a plus sign down here and a minus sign there, which is consistent with the original voltage source. Okay, so in order to compute the value of that new current source, we need to divide the original voltage value by 4 ohms using the idea of source transformation. And that V1S was 7 angle 0, so divided by 4 will just give us 1.75 or 7/4 basically. Angle 0, since this doesn't have the resistor doesn't have a phase angle. Now we have 2 current sources in parallel. We also have 2 resistors in parallel, but here it's just choosing to do the current sources first. And those can be combined, but you have to always think about, when you combine current sources, do they have the same sense or opposite senses? So here this one is pumping charge from the bottom to the top, neglecting the fact, of course, it's really AC and going both ways, but in terms of the defined polarity, it's going from bottom to top, and this one is going from top to bottom. So it's doing the opposite of what this one is doing. Therefore, those are fighting each other. One is sending charge up, the other one is sending charge down. They're fighting, and therefore they have to be subtracted when we combine them. So we'll, for example, keep this source in its direction, and then subtract off the value of this source. So we're going to have the I1S, which is the 6 angle 60 degrees amps, and then subtract the value of this source, which is the 1.75 angle 0. And that calculation needs to be done on a calculator because the result is not obvious. It's basically a vector subtraction type of problem. And that'll give us this answer. So that becomes the value of the new source, the I3S, and that's noted here. And then we can combine those 2 resistors in parallel, which is very simple, just the product divided by the sum. So that works out to be 8/6 or 1.33, 4/3 in other words. And now that's all that we can combine in series and parallel, so we'll do another source transformation to change the current source in parallel with the resistor into a voltage source in series with the same resistor. So the V2S is not affected here, but the V3S basically is the product of the current and the resistance. So I3S times 1.33, that calculation is done here. That's that 5.34 angle 76.5. Since we're multiplying by a real number, that's quite simple. It just changes the magnitude. Now remember, if this has a phase angle, then we have to add the phase angles. But here the phase angle is 0, so that still has the same phase angle in the product. And this would be done usually on a calculator. And having done that, then we also check the polarity, meaning the head of the current arrow should correspond to the positive side of the new voltage source. And then the 1.33 has just been moved down here for convenience, but it is in series with that voltage source, so that's acceptable. Okay, and then we have two voltage sources that are in series, and so those can be combined into a single voltage source in order to use the voltage divider formula for a single loop circuit. It is already single loop, but we want to have just one voltage source to use the voltage divider formula. So we can combine those, and again we have to think about polarity as always in circuits. So we need to think about, are these doing basically the same thing or fighting each other? Well, this one by itself would cause current nominally to flow from the plus to the minus, in other words to go counterclockwise. This would do the same thing through the passive elements. It would flow from the plus to the minus, also counterclockwise, so those two are adding. It's much like if you put two batteries in a flashlight, you would want the negative side of one to touch the positive side of the other in order to add the two voltages. Now remember, of course, these are really AC voltages, but when we're doing the computations, we just treat them as DC as far as the polarity is concerned. We just add those two numbers, and those again are complex numbers here. This 8 angle 135 and 7.13 angle 76.5. So adding those in a calculator would give you this value. And that becomes what we call V4S here. And now we have a single loop circuit, so that can be solved now easily using the voltage divider formula since we have only one voltage source. So we take the value of that source, which is now the 13.2 angle 108, and multiply now times the impedance whose voltage we want in the numerator. So that's going to be Z1. That's this value. It goes in the numerator. Also goes in the denominator, and then we have to add to it the other impedance whose voltage we do not want, which is the 1.33 ohms here. And then, as always, we need to check the polarity of any formula, whether it's Ohm's law or anything else. And here we think that the positive side of the voltage source is connected to the positive side of E0. The negative side is connected to the negative side. So those do, in fact, have the same sense. So in this case, we need a plus sign in front of the voltage source here. But remember, about half the time, if either one of these things were reversed in polarity, we would need to have a minus sign there. So it's always very important to check the polarity. So having the formula now, we can just evaluate that straightforwardly on a calculator using complex numbers. And in polar form, that would be 10.3 angle 100. And then we do the inverse phasor transform using the, in this case, it says F equals 1 kilohertz. So we need to use omega multiplying t, because what multiplies t is always omega by definition. So that has to be the angular time frequency, since the natural argument of radians, of course, or argument of cosine function is radians. And so we have to multiply this by 2 pi. Remember that omega is 2 pi f. So that would basically be 6 pi kilohertz. And multiplying that out, that works out to 6,280. And again, that's just written as a simple decimal there. And then we put the phase angle from the phasor and the amplitude from the phasor, and that would create the time function, which is a function of time. Okay, so that's the example problem. Now let's actually work a problem to illustrate all the steps. So again, this is a source transformation problem, and so we must therefore use the circuit editor to try to get this down. The only type of circuit that's going to let us analyze is either single node pair or single loop. So we're going to try to get it down to one of those two forms. Doesn't matter which one. So we click the Simplify Circuit button. And now we have to study this a little bit. And similar to that example, we actually have two elements in parallel here. And because of that, those two things are both passive elements. They can be combined. That will not disturb this sought voltage V0 because V0 appears already across both elements, and so that won't be affected. So to combine those two things in parallel, we could use product over the sum, which would be negative J21 over 3 minus J7. That's probably the easiest way to do that for simple numbers like that. So let's use a calculator. So I want my result to be in rectangular mode, and of course I have to be sure that I'm not set to real here, otherwise no complex number calculations would work correctly. So I'm going to change the mode to rectangular mode for right now. So I'll come down here to this line, and I have a choice of either real calculations or, in this case, I want rectangular. So I'm going to click enter to select that, and then clear, and that puts me in the proper rectangular mode, as you can verify up here. Okay, so now again that's negative J21, and I need to put I in the calculator, so that's the second plus period, 21, divided by the sum, which is 3 minus J7, and I need to, of course, put that in parentheses because otherwise the order of operations would not give me the right answer. So it's 3 minus I7, and it does use implicit multiplication on this calculator. If you don't have that, you would need a multiplication sign. Okay, so that's the, just checking that, that's the product divided by the sum, so that should be correct. So now I just hit enter, and that's in rectangular form, so I'm going to enter that here to replace this impedance. So that would be 2.534 minus J 1.086, and then I will remove or delete this other element here. Since it's in parallel, we always delete it. Now notice this is red. That's because this value is invalid for a pure capacitance. So we need to change the symbol there to a generalized impedance, which we do like that. Otherwise we'd get an error. And now we check that combination. Remember, you have to check each step in the circuit editor. And remember, you always have the circuit in the previous step here for reference displayed in case you need to check that, especially when you're doing source transformations. That's very handy. So we'll check that. That is correct. I'll go back to full screen here. So now let's see. There's nothing we can combine here. I don't see anything else in series or parallel. So now we're going to have to start doing a source transformation. And unfortunately our dialog box here has gone astray. That's because I'm using reduced screen size. So I'm just going to go out of the circuit editor and go back in. It'll fix that. A little workaround here until we get that fixed. Okay, so we need to do a source transformation, and remember that we cannot transform this source and impedance because that would disturb this sought voltage V0. So we can't touch that at all. If we try to touch that, we'll get an error because that's not going to be permissible to preserve the sought voltage. So instead we have to transform something else. And the obvious thing here would be to transform this voltage source that's in series with a resistor. Now you could say, well, you have a current source in parallel with a resistor, you could transform that, but we always need to think about, is that useful or not? And that would actually not help at all in terms of simplifying the problem, because then we'd have a voltage source here and a resistor here, and that doesn't allow any further simplification. So that would not be a good thing to do. Instead, we want to do it this way. So to do that, I'm going to drag that voltage source over here to a new position, and then I'm going to add the wires. Well, I'm going to change it to a current source first, so I'll change that to a current source. And then we need to enter the value, which is going to basically be 5 angle 0 divided by 6. So that's one we can easily do in our head. 5/6 is, let's see, 0.833. If I remember correctly. And then that would be angle 0, because everything is basically a real number there. And then we need to add some more wires. So I'll click Add New, and by default that's going to be a wire. So I'll place a wire there and there and there to properly connect things. And that should be, yeah, that should be good now. And now I need to check also the polarity of the current source, because remember this plus sign is here, so that should correspond to the head of the current source. So I actually need to reverse the polarity on that current source to have a correct value there. So I want the head of the current source to be where the plus side was on that side that's more positive. So I need to do that, and now we'll check the source transformation. That is correct. And now we see that we have some things in parallel. We have two resistors in parallel, so let's just do that. So the product over the sum would be 3 times 6 is 18 divided by 9, so that would just be 2 ohms. So we can replace that by 2. Don't even need a calculator for that one. And then we can just delete this, because that's going to be absorbed into this basically now. So we're replacing 2 resistors by 1. So this one, of course, we never change that to a short, because that would basically say that the original 2 resistors were equivalent to a short, and that doesn't make any sense. So we always have to delete that. And we'll check that combination, and that's correct. And then our 2 current sources, we can combine those by adding their values. Now, since these are complex numbers, we'll need to do that using a calculator. But we first need to figure out, do we add them or subtract them? Well, we have to look at the sense of the 2 current sources. So this one is pumping charge from the bottom to the top nominally. Now again, it is really an AC source. It's actually going both ways. But for purposes of polarity, we consider it going from bottom to top. And then this is doing the same thing. It's pumping charge from the bottom to the top. Therefore, since both of them are pumping charge from node A, say, to node B, they're both helping each other rather than fighting. So that means we add their values to combine them as opposed to subtracting their values. So let's go to our calculator now, and we'll add 3 angle 60. And now I want this result to be in polar form. So before I do that, I'm going to change from rectangular back to polar form. So I'm going to go to mode here, go down to that, and go over to polar form, and enter that, and clear. So now I'm in polar mode, as you can verify here, because that's how I want the answer to come out. And I do want it to be in degrees, because that's the format I need here. So I have it set to degree mode. And now I need to go 3 angle 60. Now, as you may remember, you cannot enter in a TI 83 or 84, you cannot enter the argument of a complex exponential directly in degrees. It has to be converted to radians. And so I've already defined this variable e that I'm going to use. So I'm going to write 3e, and that e already was defined and stored as little e to the I pi over 180. So if I raise this to the power of my angle, which is, let's see, that was going to be 60, then that'll automatically take care of that degree to radian conversion that's required by this particular calculator. In the TI 89, you don't need to do that conversion. It would just obey the normal degree in radian mode. But unfortunately, Euler's identities do not hold for this calculator. That's sort of a defect in the design, if you will. So that plus now the 0.83 angle 0. So I just have 0.83 basically. I don't need to enter the phase angle if it's 0. And click enter, and that gives me the value directly there in polar form. And if you want to make sure that's reasonable, you can imagine, well, you've got 3 units to the right. 3 units going up at an angle of 60 degrees, so sort of like that, and then a little bit 0.83, so you can kind of imagine how that angle, so something, the angle in between those two is reasonable. So that's a fairly reasonable result for that. So let's put 3.490, just 3.49 will be good enough there, and then the angle will be 48.1. And then the other current source needs to be deleted because, again, its effect is going to be absorbed into this one. And we need to reduce that to a 0 value current source, which means an open circuit, not a short. Again, if you shorted it, it would be like the original current sources weren't even there. So that would make no sense at all. So we have to delete that. I'll click the delete button up here. And now we can check that combination. And that is correct. So now I'm going to go back to full screen here. And again, just my dialog box ran away. I'm going to just click Done Editing and go back in just to fix that. Okay, so now we need to do one more source transformation to make this into a single loop circuit. So now we can transform this current source in parallel with this resistance into a voltage source in series with the same resistor. So I'll just go here and change that to a voltage source. And I'm right away going to change its polarity because, again, we want the head of the current source to match the plus sign on the voltage source. And then I also need to get rid of that. So I'm just going to press the delete key here to get rid of that. And then move, or just, oh, well, it wants me to fill this in first, I guess. So, all right, I'll fill that in before I do that dragging. So I need to multiply this. I basically take IZ is the value of V. V equals IZ is the relationship here. So I need to multiply that by 2. So since 2 has a phase angle of 0, that won't change the phase angle at all. So that'll still be 48.1 degrees. But this will be, let's see, that will be 6.98, doing that in my head. So 6.98. And now I can drag this up there. And that should complete the source transformation. So again, I just multiply this by 2. And we'll check that. And that is correct. And now the last step here will be to further simplify. So it already is a single loop, but I'd like to combine the two voltage sources at least so that I have a situation where I can use the normal voltage source, voltage divider formula. Now notice we have to see, are these two voltage sources helping each other or fighting each other? So if you just think about this one, with this one shorted, that would cause current to go nominally from the plus side through the passive elements to the minus side. In other words, water flows downhill, if you will, from a high point to a low point. So that would be going clockwise. If we shorted this one, though, this one would make it go counterclockwise, because here we're going to go from the high voltage through the passive elements back to the low side. Again, water flows downhill through passive elements. And so that's going to go counterclockwise, which is the opposite of this one. And this is, so that means they're fighting each other. And it's much like if you put two batteries in a flashlight the wrong way with the two positive sides touching, then of course that wouldn't light up your bulb because the voltages would cancel out. So I need to subtract, and let's, for convenience, keep this one because that'll have a positive sign convention compared to the V naught. So I'm going to add these two. I'm sorry, subtract this one from this one is what I meant. So we'll do that on a calculator. And so now I need to, again, I want the result here to be in polar form since I'm computing a source value. So I am already in polar mode, so that's good. And I'm going to enter 6.98. Times that E variable I defined that basically allows me to use things in degrees. And I'll raise that to the power of 48.1. And exit that template. And then I need to add, I'm sorry, I meant subtract, so we'll go back and delete that and make that a subtraction. And I need to subtract the 7 angle 165. So that would be 7. And then we have another E raised to the power. And don't forget that raising to the power or this won't work properly. So we have 165 there. And just click enter there. And that gives me the value to place here. Now remember, it has to go here, not here, because we subtracted this one as opposed to subtracting this one. So this one has the same polarity as our answer. So we need to use this source for the answer. So we have 11.91. And then the phase angle there is 16.5 degrees. And then this one, importantly, we need to change that to a short so that we basically transfer its voltage into this. And now we can check that combination. And that is correct. And so now, basically, we're done with that. And so now I'm just going to say I'm done editing here, because that's suitable for a voltage divider formula. So now we have the edited circuit, which is suitable for voltage division. So we're going to use a single loop analysis. And we want a SOT voltage, so we'll pick SOT branch voltage here because it's across one element. And now we can say V0 is equal to, and I'm going to use the standard voltage divider formula. If you just want to put in a numerical answer directly, you could use this term instead and compute it on your calculator, and that would save a step, but I'm just going to enter it here so that I can have my work checked in more detail. And the value of that source now is 11.9 times 16.5 degrees, or rather angle 16.5 degrees, not times. And then the impedance of interest is the one that goes in the numerator. So that will be the value of Z1. So that's 2.53 minus J 1.09. And then we'll just copy that and paste it down in here. And then the other impedance would be just the 2 ohms. Now, before I check this, I want to make sure that I have everything correct. And one of the things I always need to check is the polarity. So I actually designed this so that we would have the correct polarity here, so we wouldn't need a minus sign. So the plus side of the voltage source is connected to the positive side of V0, and the negative side is connected to the negative side. So that matches, and therefore it's going to have a plus sign here rather than a minus sign. But again, we always need to check that because that's an easy way to get a wrong answer. So let's check our equation. And that's correct. And that's the only equation we need. So we click no more equations here. And now we simply need to compute this value using a calculator. So we'll enter 11.9. And then we'll put that E. And I'm still in polar mode, by the way, which is what I want the answer to be, so that's good. So 11.9, let's see, E 16 to the power 16.5. Got to remember to use that power key, otherwise I'll get a very wrong answer. And that needs to multiply, open parenthesis, 2.53 minus J, or in this case I, 1.09, close parenthesis, so that's the numerator. And then we divide by the denominator, which I'll open parentheses there. And so just adding that in my head, I can see that that's 4.53, just to save a little writing here, minus J 1.09. So minus I 1.09. And close parentheses for the denominator. And that should be correct. So now I just press enter. And that should be the resulting value of V0. So let's enter that here. So it's 7.036. And then the phase angle will be 6.721 degrees. And we'll check that. And that is indeed correct. And so the last step then is to do the inverse phasor transform to find the resulting voltage in the time domain. So we're given the cycle frequency here in kilohertz, so we need to convert that to a mega because this thing that multiplies t is by definition a mega. So let's use our calculator to do that before I go out of the calculator. So that's 0.9 E3 for kilohertz, or I could have written 900, either way. That times 2 times pi. Just remember that omega is always 2 pi f. That's a formula you should memorize. Okay, so that gives us 56.55, say. So I'll just put that over here. And then we put the magnitude here, the 7.04, now becomes the multiplier of the cosine function of time. And the phase angle here is 6.72 degrees. And so now we just check that. And that is correct. And it's asking us if we want to see a detailed explanation of this, which I'll just show you in case you want to see that. And basically it just shows you how to do the voltage divider again in case you had any questions about that. So that concludes this problem.